Okay, class, here we are back again for another 30 or 40-minute session on the Rankine cycle. Exciting stuff, riveting, I know. So let's move on. This is a little bit of review. We said this subsystem B is really those components, the steam generator, where the heat transfer is added to the working fluid, the turbine, the condenser, and the pump. That cycle is what we call the Rankine cycle. That's about as simple as it gets right there. That's what, and we have the little ball that circulates around through it. Oh, that's nice. No, I didn't program this. I stole it mercilessly. Okay, so let's back from our Thermo 1 days. We would talk about the first law, and requires that for a cyclic device, a power cycle, that the net work developed by the system undergoing the cycle has to equal the net heat added by heat transfer to the system. So cycle work, and the dots indicate those are rates. So the rate of work being produced by the cycle equals the net rate of heat transfer into the cycle minus the net work of heat transferred out of the cycle. So you subtract those two, and that has to equal for a cyclic device. And the cyclic device doesn't have to be irreversible. It can be reversible or irreversible. There's no requirements on that. The thermal efficiency of a cycle is then the net work. That's the reason that we run the cycle, to get the work out, divided by the costly input, which for a lot of power plants could be coal or natural gas or uranium that goes into the fuel rods, etc. So, okay. The second law of thermodynamics also places requirements on us, and one is that the efficiency has to be less than 100%. You can't get more energy out than you put in. That would be a nice trick, but nobody has figured out how to do it yet. Maybe thermonuclear, I don't know. We actually convert some mass, but I don't know. But we're not doing that. We don't have thermonuclear power plants that like explosions where we convert mass into energy. Okay, most of today's vapor power plants have efficiency ranging up to about 40%. We'll see that combined cycle plants, which would be the Brayton cycle mated to the Rankine cycle, have efficiencies that can exceed 50, 51, 52%. But most of the standard just Rankine cycle plants, I would say the efficiency is between 31 to 35 on a good day, and very few of those supercritical units can approach 40. But most of the units are not supercritical in nature. Thermal efficiency tends to increase as the average temperature at which energy is added by heat transfer increases. So if we can transfer the heat in at a higher temperature, then we can get a higher thermal efficiency. The average temperature at which energy is rejected, if it decreases, then we can increase the efficiency of the cycle. But our heat rejection is usually to the atmosphere, either directly to the air or to a lake. So if it's to a lake or a river, then the only way to make that condensing temperature lower is to get cooler water. And how are you going to cool the lake down more? That's just about impossible. You can't run around throwing chunks of ice in the lake. There's going to be no payback on that. So, you're kind of stymied on the low end. I mean, if you had an air-cooled condenser with, say, cooling towers, and you went to a body of water which was colder, then it would help. But if you had a body of water where you built a plant, then you wouldn't have bought the cooling towers in the first place. So, this is theoretically nice, but in general, it's harder to do. On the high end, we're limited somewhat by materials that can exist for long periods of time at higher and higher temperatures. So the high end is a materials constraint usually, and the low end is an environmental constraint. Improved thermodynamic performance of power cycles as measured by increased thermal efficiency, for example, also accompanied with a reduction in reversibilities or losses. Yeah, so if you had, let's say, the turbine, you didn't have any insulation on the turbine, even though that would still be pretty small, you could insulate the turbine. You could insulate steam pipes that were carrying high pressure steam from the boiler to the turbine, hold more heat in, and that would put a little more energy into the turbine, and you get a little more out. That would help your efficiency. Reversibilities, if you had, the turbine bearings were rubbing or somehow inefficient, and you fix those, you would reduce the reversibilities and you would get more power, and it would help your efficiency. In general, this is still pretty hard to do, but because plants are designed with this in mind, but it's not impossible. The extent of improved power cycle performance is limited, however, by constraints of thermodynamics and economics. Economics are big. There's a lot of things that potentially we could do, but if the payback is bad, then the business case would not be particularly good, and it probably wouldn't get done. Okay, so let's take a look at the Rankine cycle itself. We see a picture of it over there. Each mass of water circulating through the interconnected components undergoes the thermodynamic cycle known as the Rankine cycle. Okay, 4 principal control volumes, and I think we know this, but there is the turbine, good looking turbine. There's the condenser. There's a pump. In Portuguese, that's bomba, by the way. And boiler, that's where the heat is transferred in through the combustion. Water vaporizes to steam, and that is what drives the cycle. Okay, sign convention. All energy transfers by work and heat are taken as positive in the direction of the arrows on the schematic, and energy balances are written accordingly. So these may violate the sign convention that we established in Thermal 1. Well, don't worry about it. We're going to calculate them as positive, and the energy flows in the direction. So the energy flows out of the turbine work. That's positive. The heat added to the working fluid in the boiler is coming in. We're considering that to be positive, et cetera, et cetera. So you can see those arrows and just recall that. Okay, the processes of the Rankine cycle are 1 to 2. Vapor expands through the turbine. So we're taking point 1 as the thermodynamic state entering the turbine. And so when it says expands, that means the pressure decreases, and it's a gas, it's a vapor for the most part. And so its specific volume increases as the pressure decreases. And the density is just 1 over that. So the density is high, goes to low. Specific volume is low, goes to high as it goes through the turbine. So the steam expands through the turbine, developing work. Okay, then we come out of the turbine and we have mostly vapor. It probably has a quality of between 93 and probably 96%, which means there's a little bit of water droplets in it, but most of it is vapor. It's not very hot. It's typically on the order of 110, I think, someplace 110, 120, because the condensing pressure is low, 1 psia. You can look up the saturation temperature for 1 psia and be in pretty good shape with knowing what that condensing temperature is. But we can't throw that working fluid away, so we have to condense it. And so the vapor condenses to a liquid through heat transfer to cooling water. Cooling water could be cooled by the lake, or it could be from through big cooling towers. Liquid is then pumped into the boiler, requiring work input. You can't get it to move without pushing it. And the way we push it is with a motor. These pump motors are typically 2,000 to 4,000 horsepower on boiler feed water pump. I think Kingston is about 3,000. They've got 2 different sizes because they got 2 different size units. And liquid is heated to saturation. and evaporated in the boiler through heat transfer from the energy source, and it's actually superheated. Not only is it evaporated, but then it's heated beyond that to drive the temperature up into the superheat range. So, engineering models. Each component is analyzed as a control volume at steady state. So we make this, certainly at least in Thermal 1, and probably most of what we do in here, as simple as possible. And so the equations turn out to be not much to worry with. The turbine and pump operate adiabatically, and that's a fancy word for what? They have no heat transfer. So adiabatic means we're just not losing any heat from the surfaces of these things to the environment. In reality, we are, but they're really pretty small terms. There's not much of an error involved in ignoring the heat transfer from a turbine or a pump. Kinetic potential energy are exchanged or ignored. Sorry. If we write the full form of the first law for steady state, we've got changes in kinetic energy and potential energy, but generally speaking, those terms are also small, and they get ignored as well. Okay, so if we apply mass and energy rate balances to draw a control volume around each one of these components, we're going to get the following. The turbine, we get the total work out of the turbine divided by the mass flow rate, which would be the specific work, or the work per unit mass. The rate of that is just the difference in enthalpy. Now, this is a simple turbine without extractions. So if you have extraction ports, then you have to do some more mathematics on it. But you would generate the expression from a control volume around whatever turbine you're working on. But for our simple turbine, it's just that the specific work is equal to the enthalpy in minus the enthalpy out. Very nice. For the condenser, the heat transfer per unit mass, or the total heat transfer divided by the mass flow rate through the condenser, is again the enthalpy difference. And so all of these, as they're written, will yield positive quantities because the energy is higher going in than coming out. And the energy that's lost in the condenser goes to the cooling water. And so we can do a balance on that as well. And the pump, the total work into the pump divided by the mass flow rate is equal to the enthalpy change across the pump. So in this case, it's going to be H out minus H in to make that positive, because as the fluid goes through the pump, energy work is done on it, which increases the energy. The temperature might go up a little bit, but the pressure will go up significantly, and that increased pressure is energy. Okay, and the boiler. So the total heat input in the boiler is divided by the total mass flow rate through the boiler is equal to the enthalpy of the exiting fluid, H1, minus the enthalpy of the entering fluid, which is probably liquid, and at the exit it's either superheated or saturated vapor, depending on what boiler we're talking about. So those are our equations. Just a bunch of enthalpy differences, not too bad. Okay, performance parameters. We have thermal efficiency, like we said, is the net work out of the cycle divided by the costly input, which would be the heat transfer rate into the working fluid by the boiler. And so to calculate that net cycle work, that's the work produced by the turbine per pound mass, divided by the specific work that had to go into the pump, and those are both positive numbers, the way we've written the equation. So when we take the turbine work and subtract off the pump work, we get the net work by the cycle, and then we divide that by the heat input to the boiler, and all of this is done on by specific quantities, so we're dividing by each quantity by the pound mass of flow. And so in this case, for the simple cycle, all those mass flow rates are the same, and so all the m dots cancel, and so then we can just plug in the enthalpy differences or I mean, by definition, it's the specific work of each and the specific heat input. So we just put in the enthalpy differences, and we get the equation for the thermal efficiency. The back work ratio is known as the ratio of the pump work divided by the total work produced by the turbine. Both of those we're showing specific quantities. And so then we can plug in the enthalpy differences for that. So how much work does it take to run the pump divided by how much work do we get out of the cycle? Okay, so back work ratio is typically very low for vapor power plants. There's some examples that are in the textbook, but it shows that the power required by a pump is typically less than 1% of the power developed by the turbine. For the Brayton cycle, because we'll see that a little bit later, but we have a compressor that's compressing air basically that's coming in, and that compressor requires 30-40% of the total work developed by the turbine. And so that's the problem with trying to, increase pressure on a vapor. It's energy, the energy required is tremendous compared to increasing pressure on a liquid like water, which is close to incompressible. You can push pretty hard and you don't change the density much, but you start pushing on air or gas or a vapor, and that's what you get. You have to push really hard, and you get a lot of heat as well as an increase in pressure. So it's just not very efficient to compress a gas compared to pumping a fluid, a liquid, in a cycle. Okay, so provided states 1 through 4 are fixed, then equations 8.1 through 8.6 can be applied to determine the performance of power plants adhering to the Rankine cycle. The equations are developed from mass and energy balances. They apply equally when reversibilities or irreversibilities are present. So for ideal or non-ideal cycles, they work. Ideal Rankine cycle provides a simple setting to study aspects of the vapor power plant performance. The ideal cycle adheres to the following assumptions. Okay, so the easiest you can get is stuff like the frictional pressure drops are ignored during flows through the boiler and the condenser. These processes occur at constant pressure. So, we're not going to have pressure drop through the boiler. We're not going to have pressure drop through the condenser, at least initially. So we may get some problems later on that are a little more complex that take some of that into consideration. Flows through the turbine to pump occur adiabatically and without irreversibility, i.e. no friction, no dissipative effects within the flow or as the fluid goes through the devices. And so adiabatic and without irreversibility means reversible. Adiabatic reversible is isentropic, and that means the entropy is constant through the device. So that's the way the turbine and pump will be handled. Okay, so ideal Rankine cycle. Ideal Rankine cycle consists of the 4 processes that we've seen. And they're all internally reversible. So there's the isentropic expansion through the turbine. That little ball, I love it. Okay, and so that's the, now we started at 1, so you see 0.1 up there, that's saturated, that's the saturation dome on a TS diagram. So that's saturated vapor, and then it's falling straight down because entropy is the bottom coordinate, and so if we're going to do that at constant entropy, we have to come straight down. The line from 4 to A to 1 to 1 prime and on up is an isobar. It's a line of constant pressure at whatever our high pressure in the system is. And then from 3 to 2 prime onto the dome and up into the superheat region is another isobar, which is the low pressure. All righty. So then heat transfer from the working fluid as it goes through the condenser is from 2 to 3. Let that little ball scoot over there. Okay, and next we have the pump, which is isentropic. So 3 to 4 is going to be at constant entropy. So it has to be a vertical line as we're going from low pressure to high pressure. So that's where we talk about it. And so the little ball is now up at 4. And then the last is the boiler, the heat transfer to the working fluid in the boiler. And we're again assuming that's constant pressure. So 4A, 1 prime is all the same pressure. And from A to 1, we're going across the dome. So we're boiling the fluid away. Possible variations on this cycle include turbine inlet state is superheated vapor. So that's 1 prime. And state 3 falls into the liquid region, which in reality it probably would, because we want to be completely liquid going into that pump. So the cycle designers are going to make sure that we're not putting some vapor into the pump and that we're fully superheated going into the turbine. Okay. Since ideal Rankine cycle involves internal reversible processes, the results from section 613 apply. Applying equation 651 to pump work per unit mass flowing through it is evaluated as. Okay, and so basically we're saying the pump work, the specific pump work, the total pump work divided by mass flow rate is the integral of specific volume times delta P. That's where this comes from. And so we're assuming specific volume is constant. And so then you can integrate, you can pull it through because we're assuming it's basically what do you call it? Incompressible. Word wouldn't come to me. And taught thermo in a couple of years. It's incompressible, and so the specific volume is constant. It doesn't change. So you pull it through the integral, and then you just integrate dP from the exit pressure 4 to the inlet pressure 3. So that's where that's coming from. But this is what I call the pump trick. And this is what we'll use on our problems to evaluate the specific work of the pumps in the cycle. Okay, so let's look at areas under process lines on a TS diagram can be interpreted as heat transfers, each per unit mass of flow rate. So area 1, B, C, 4, A1 represents heat transfer to the water flowing through the boiler, right there. So that area on a TS for this ideal Rankine cycle. Okay. Then area 2BC 32 represents heat transfer from the water flowing through the condenser, or the heat that's rejected, like this. And the enclosed area 1, 2, 3, 4, A1 represents the net heat input, or equivalently the net work from the cycle. So that's that. Okay, so ideal Rankine cycle on the TS diagram, you have the area representations. Okay, using the ideal Rankine cycle to study the effects of we're going to vary different items in the cycle, and we're going to see the impact. And I think I'm going to stop this one at this point because, again, I don't want this to get too long. It makes uploading difficult. And so we'll pick up here on the next one.